A couple quick examples that should help you with uh, using sine, cosine, and tangent for angles that are not between 0 and 90 degrees. We're not going to do a whole lot with it, just kind of lay the groundwork. So here we have some point over in quadrant number 2 over here. I know that that point is 12 units away from the origin, and I know its y-coordinate is 3, but I don't know its x-coordinate. So I want to figure out what the sine, cosine, and tangent of the angle that would get me there is. And so the angle could be this angle right here. We could call that theta. We don't have to call that theta. Maybe theta comes around from the other direction there. Maybe it goes all the way around the circle and then it goes to there. Whatever, as long as it's a coterminal angle that ends up lying on this line and going through whatever this point is, it doesn't matter which angle we are thinking of. They're going to have the same sine, same cosine, and same tangent because x, y, and r are going to be the same values for all the angles. So we'll just focus on the blue angle here that goes from the positive x-axis counterclockwise and stops when it gets to the other side of the angle, the terminal side of the angle. We need to figure out sine, cosine, and tangent. Well, sine is the y-coordinate divided by r, and we know both of those. The y-coordinate is 3, r is 12, so it's 3/12, which we could simplify to 1/4. Cosine is x over r. I know r, but I don't know x, so I got to figure that out before I can finish that one off. Tangent is y over x. I know y, but again, I'm left not knowing what x is. So let's figure out what x is. Remember that the relationship between x and y and r is that x squared plus y squared has to equal r squared. If we made a right triangle here, the length of this would be x, the length of this would be y, and that hypotenuse is r. So we've got x squared plus 3 squared, so 9, equals r squared. What is that? That's 144. Subtract 9, and we've got 135. And we could, if we wanted a decimal, we could take the square root of 135 to find out what x is. But I don't want the decimal. I'm going to get it as a simplified square root. So if you don't remember how to do that, we do a factor tree. 135 divided by 5 is what? That's 27. 27 is 9 times 3. 9 is 3 times 3. Now the bottom of all my branches are prime numbers, so I'll stop. And I see a pair of 3's, and then I've got an unpaired 3 and an unpaired 5. That means the pair gets to be outside the square root, and inside the square root, inside the radical sign, are going to be the things that were unpaired. So the 5 and the 3 multiplied together are 15. X is 3 times the square root of 15. But wait a minute, we're in quadrant 2, which means x has to be a negative number. Well, we took a square root. There are actually 2 square roots of 135. There's positive 3 square roots of 15, and there's negative 3 square roots of 15. Because we know we're in quadrant 2, we know we want the negative answer for x. Negative 3 times the square root of 15. That's our x coordinate. Now we can put that in. Negative 3 times the square root of 15. Negative 3 times the square root of 15. For cosine, I've got a 3 on the top and a 12 on the bottom. We could cancel that, and our answer becomes negative the square root of 15 over 4. For tangent, we can cancel our 3's, and we get negative 1 over the square root of 15, but we'll rationalize the denominator, which is what we call it when we get rid of any square roots on the bottom. Multiply by the square root in both places, and we get negative square root of 15 over 15. There's the sine of our angle, there's the cosine of our angle, there's the tangent of our angle. Okay, another example of something a little bit different is I've got the angle negative 2,462. And a number that big, I don't know where that's going to be. Which quadrant's that going to fall in? So one thing we could do is we could just keep adding or subtracting 360 to this until we get to the right number. But I'm going to show you a shortcut that might help. We're going to, instead of just adding or subtracting 360, because that can be time consuming, we're going to take our number and we're going to divide it by 360. And we get this, negative 6.838 repeating. What that means is the negative just tells us we're going in a clockwise direction. The 6 in front of the decimal place says we do 6 full circles. We go around the circle 6 times, and then the rest of it is how much of a circle, what fraction of a circle we do the rest of the way. So the negative 6 means we're going to do 6 circles here. Let's draw that in. So we're going to go 1, 2, 3, 4, 5, 6. There's my 6 circles. I've taken care of those. I don't want them in my number anymore then. So I'm going to get rid of this negative 6 out front by adding 6. There's how much of a circle I have left. Well, how many degrees is that? Let's take that times 360. And it's negative 302 degrees. So I've done my 6 circles. Now I need to go negative 302 degrees. There's negative 90, negative 180, negative 270, so 302 is 32 more degrees. I'm going to end up right about there. And this, whoops, this is my terminal side of that angle. There's my negative 2,462 degrees. I end up in quadrant 1. So the method was take this divided by 360, then get rid of the number in front of the decimal place, and then multiply by 360 to find out how many degrees are left. Because when you get rid of the number in front of the decimal place, you're just getting rid of the circles. Multiply by 360. But what's nice about this is when you do this division, that number that's in front of the decimal, that tells you how many times you went around a full circle.